Okay, before we start filling in some blanks, we can try and understand, maybe strengthen our understanding of what a radian is. This circle has a radius of 1. When the arc length on the outside is the same as the radius, that's the definition of an angle of 1 radian. It happens to be approximately this many degrees. You can think of radians. Radian measure is how many times you're around the outside with the radius. If you say an angle of 5 radians, you've gone 5 radii around the outside. And I won't be able to stop on the right number there, but pretty close. Okay, the distance around the outside is 5 of the radii. That's what a radian is. Regardless of how big this circle is, if I make the circle twice as big now, it's still 5 radians. It means that this distance here, this 2, is 5 times around the outside. If you had a string that was as long as this radius here and you put it around the outside, you can go 5 times around there. That's what an angle of 5 radians is. It's called radian because radii. Okay, now I'm a bit off there, but 10, whatever units these are, 10 centimeters maybe, and this is 2 centimeters. You're 5 times as far as this radius around the outside, so 5 radians. It happens to be that many degrees, but we're going to use that idea in this arc length formula. We want a formula that relates this and the angle in radians. In radians, it's pretty easy, right? The relationship between that, now again I'm off, it's 10.01, see if we can make it exactly 10. How are these things related? As in, I can't put them all together here, but maybe I can almost put them all together. Can't move this over there. Close. How are those related? If I change these now, so if I do this, how is the arc length related to the radius through that angle? What formula could you write? Wherever I go there, this arc length is equal to what?
2R.
Yeah, 2 times, well, not 2. If this number happens to be 4 right now, let's just use the variables here. The arc length and theta and the radius. How are all those related to each other? Let's try a different number here. Number we can work with there. That's good numbers. Yeah, it's just this times this, right? Regardless of how big the circle is, if we change this now, if we change it, let's actually make it bigger like that and then zoom in on it a bit. Okay, so the circle has a radius of, get that out of the way for now. The circle has a radius of 4. If I have an angle of 3 radians, which is just before pi, right? Halfway around is pi, 3.14, so angle of 3 radians is just a little bit less than that. If you have a radius of 4 and an angle of 3 radians, the arc length is 12, because that's the definition, right? That's the definition of what a radian is. An angle of 3 radians means you do 3 radii around the outside, right? So it's 4, another 4, another 4. If you wanted, you can, I don't know if I can manage to do this, but if I put this somewhere in here, that's about 1. Oh, maybe it won't let me do that. Why won't it let me do that? Oh, whatever. Anyways, never mind. However, big you make this, that's the relationship between those things. You could write a formula for how the radius and the arc length and the angle in degrees are related, but it's not going to be as nice of a relationship as we just had, right? If you make it, let's again go back to some nice numbers here, like if you make the arc length 10, if I can, this always makes for a great YouTube video, watching me do that. If you have, this is 4 and this is 10, how is it related to this? It is related to that, but it's not something you can kind of work with in your mind. This you can work with easily, because you can say, if the radius is 4 and I have 2.5 radians, the arc length is 10. We could write a formula for this, and we will in a second, for how these are related to the arc length, but it's not going to be as nice. Okay? To write the formula, you're just going to write a proportion. If I'm halfway around, the arc length is half the full circumference. this angle here should compare to the full turn angle the same as the arc length compares to a full circumference. Okay, if the angle is halfway around, the arc length is half of the full circumference. Wherever I am here, if I'm a quarter of the way around, this is a quarter of the angle all the way around. This is a quarter of the circumference. So you're just using a proportion like that, right? Proportionally, the angle compared to a full turn is the same as the arc compared to a full circumference. All right, so now you can get excited because we're going to fill in some blanks, but the arc length is part of the full, I don't know, circumference. All right, so if you have a circle, what we're saying is, make this big enough so you can see it. Okay, so there's an arc, sort of. Not drawn very well, but there's an arc on a circle. If you draw the angle in the center, this angle compared to the full turn. Okay, so these are proportionally the same here, right? The angle here, that angle in the center compared to the full turn angle is the same ratio as this arc compared to the full circumference. Okay, so central angle subtended by the arc is part of one complete, I don't know, rotation, angle, whatever, one complete going around the center of the circle once. The proportion then is this. Okay, this is a proportion, right? A proportion is just, A over B equals C over D, something like that. Right? Proportionally, 2 compared to 5 is the same as 4 compared to 10. That's a proportion, right? You guys learned in grade 8 you can solve proportions if there's a missing number like that, right? You can solve if you can write a proportion between two things, you can find the missing value as long as you have a fraction to compare it to. So the fraction we're comparing it to is to a comparison that we know. The arc length, which is called A, over the total circumference, which is 2 pi r, right? Pi times the diameter, or 2 pi r. That should be equal to the central angle, which we're calling theta, over whatever one full turn is. If we're using radians, how do you write a full turn? What's a full turn if we're using radians? 2 pi, right? This is 2 pi here. If you want to take this formula, you can simplify it. Right? You can manipulate some things. If we wanted A to be all by itself, just like any other formula you can solve for things. If I take A over 2 pi r and I have that equal to theta over 2 pi, you could multiply both sides by 2 pi r, or some of you think of it as, well, this would just move up on the top on the other side, right? You're okay with that? However you solve proportions, you can end up with that. I guess we don't need that line anymore. What can I do with that to make it simpler? Yeah, that stuff, just theta r. So that's the same as what you kind of hopefully could see, or r theta, theta r. That's the same as what you could see just kind of intuitively from the picture. If you want to know the arc length, as long as you know the angle in radians, sorry, move that. As long as you know the angle in radians, try again, and you know the radius. So if you have a circle that is a radius of 3, and you have an angle of 4 radians around to there, what's the arc length on the end? What's this arc length then? 12, right? It's just 12 because that's the definition of what 4 radians means. It means you've got 3 and 3 more and 3 more and 3 more. That's what a radian is. It's saying how many times are you putting the radius around the outside. This is what the formula looks like if you're in radians. It's not so nice of a relationship if you're in degrees, which we can look at right now, but I have to stop this first.